Okay, good morning to everybody. Thanks, Konstantinos and PAINLESS for this invitation. So my talk is entitled Reconfigurable Intelligent Surfaces for 6G Wireless Communications, Localization and Sensing. It's actually a topic that I've been working the last nearly 4 to 5 years. Started working on that while being in the industry some years ago. And we're going to discuss actually the application of this technology in communications, localization, and sensing. During this presentation, I'm trying to highlight the relevant works of the things that I will discuss. I'm not going very deep technically. The reason is only one. I want to provide actually the wide bandwidth of this technology, which is actually envisioned to solve, to treat various recent problems. Of course, in parallel, I will be critical, because certainly it's not the topic that will solve the solution that will solve all our problems. So you know already very well that there are various applications of wireless communications, and here I'm borrowing some figures from various industrial partners that actually go far from the typical cellular application of communications. And here you see that we have actually wireless systems nearly everywhere. And the trend is going to be even more pronounced in the near future. So of course, we know well that we have various applications in, let's see if it works, in self-driving cars, in smart farming, probably sounds like an extreme application. Of course, Industry 4, which drove all this hype of 5G, which is actually a reality right now. And of course, the smart homes that we know for a couple of years, but recently we see them actually really happening. Of course, all of them, they rely, if we're thinking about 5G and 5G technology, on these key use cases, this enhanced mobile broadband access, where we're seeking about high rates, the ultra reliable and low latency communications, where we need very high reliability and low latency, and certainly this massive machine type of communications. And you can easily identify that all of these use cases and items are actually being, let's say, elaborated in the applications that you see here. Currently thinking about the 3GPP releases, I've downloaded a very recent, the latest actually timeline from 3GPP, where you see where we actually are. Actually, the release 17 was frozen in March 2022. I mean, nearly a month ago nearly. And now the technological focus is release 18, which is already named as 5G Advanced. If you recall, we have this LTE and LTE Advanced in the past. This is when I started doing my PhD, my postdoc together with Professor Papadias some years ago. So release 18 is about to identify, now the discussions have started, all the key technologies for going further. And here you see the content of this release, identifying various priorities of the different working groups. And I want to emphasize the RAN part, which is actually my expertise. And this is actually, my talk is mostly focused on the radio access network, where you can easily identify that we still have, and actually we have the evolution of the MIMO technology that actually started theoretically in the early 90s. Konstantinos actually was involved, one of the first works on this topic, going back to Jack Winters. And you can also identify the trend, which is actually a reality already in artificial intelligence machine learning, that apart from the network orchestration also emphasizes on the RAN part. And I want to zoom in a little bit on this smart repeater, which seems to be, let's say, the working force of the reconfigurable intelligent surfaces. It's actually a concept being pushed, if I'm not doing wrong, from Qualcomm 1-2 years ago. And it's actually, in a way, evolving this technology of relay, which has been even from 4G under the standard, but not really emphasized and applied in practice. I will also, at this point, I will rephrase a little bit what I heard some years ago from a famous professor working in MIMO that said that Massive MIMO is the actual application of multi-user MIMO. Those years back, we were working on interference alignment. I feel that the RIS technology, at the end of the day, will be the enabling technology to realize relays. Of course, I will identify which are the differences, but at the end of the day, the way that is being pushed is under this smart repeater terminology. Have this in mind. Going a little bit back, just to see a little bit this evolution of the wireless generations, going from 1G to 5G and the 6G discussions. What I want you to see here is that we're going towards more massive MIMO deployments, which means that antenna arrays that have much larger number of antennas. Of course, we go over densification, which means that the distance between, actually the distance of the wireless link gets smaller, and we're going towards higher frequencies, which is, let's say, the next hype, although not really fascinating in the sense this is something that's happening in the last years. We're going higher and higher. Let's see where we will end up at the end of the day. Of course, there is certainly this need of having intelligent algorithms to learn, predict, and adapt. But emphasizing on the massive MIMO technology, what certainly we need is to have cost and power efficient transceiver hardware. So in a way, I would like to, let's say, position my talk here around this aspect, having efficient power and cost efficient transceiver hardware realized either for reception or transmission or for relaying information, right? In the sense that will be identified later on. Before going to the outline of this presentation, of course, I would like to speculate some of the early requirements for 6G networks, not by me, but by various people in the field, where, of course, we need this huge amount of this peak data rate. The positioning accuracy is, of course, much stricter compared to the past. The radio latency, there's a trend, of course, trying to go even lower for all these mission critical applications and various other things that you can easily see here. I emphasize the learning, prediction, and adaptability of networks. But a key question here is, can we continue scaling the number of antennas and densification, which seems to be the trend? And because we know well that there are issues in terms of cost and power consumption of the antenna array. And of course, densification doesn't come only with profits. There is this major issue of creating interference, which we have to deal. And to deal with that efficiently, we have to rely on sophisticated algorithms, which at the end of the day, they require control, which is a major issue. If we can do that, certainly we need power and cost-efficient transceiver hardware, as I said before. So let me go with the outline of my talk. I will start with the definition of the smart radio environments, which they include, let's say, a new item into the picture of networking. And then we're going to discuss the hardware architecture for this technology, which are actually various. Then some fundamentals on the and modeling of the unit cell, which is the basic element of a reconfigurable intelligent surface, and the received signal model, which is of paramount importance to devise signal processing algorithms. And then some applications of RIS-enabled smart wireless environments with some very brief conclusion and research directions. So starting with the smart wireless environment, what is it? This is actually taken from a joint work from various people, including myself, some years ago for what is really happening on the network. So here you see a typical, let's say, outdoor network deployment, where are the base stations, there is a UE, there are obstacles in the environment, and the RAN is actually capable of identified in the case where the UE requests for service, identifying which is the most preferable in terms of received signal strength base station, for example. And there are certain signals here that are being measured, and at the end of the day, the user, the system, decides which is the base station to be served. The vision of having, and what is actually clear here is that the obstacles, they determine the wireless propagation environment, and they can actually help us or, let's say, damage us in terms of signal propagation over the air. I mean, there are going to happen reflections, which we cannot really control. So there is a major entity, the channel, whatever between the transmitter and the receiver, which is totally uncontrolled. The vision of having environments which are programmable, it's actually to code various objects of the environment with hardware, very simple hardware, that give us the capability to determine, to design at will the reflections. So in this way, the environment could be programmable. How we can do that? Actually, we can do that with the technology of Metasurfaces. It has various acronyms. I will try to list them all afterwards. But the main idea is that compared with the environment up to now, which is totally uncontrollable and is being determined by the geometry of the environment, the idea is to code objects of the environment with hardware which is low power, very cost efficient, and can help us control the reflections. Sounds cool, but how can we do it? Actually, there are available metasurfaces in other fields, starting from imaging, etc., that are available from few megahertz to terahertz, and they actually operate at the basic level of the propagation waves, and they are capable of tuning the impinging electromagnetic field in the RF domain. Here you see a metasurface, there is an incident wave, there is a reflective wave, and this is usually comprised by unit elements, which are called cells in principle. And what is really happening is at the end of the day, apart from being, let's say, determined only by geometric physics, Snell's law, to have the reflection, you can tune the reflection. It's like having a beamforming in a way by elaborating this with these elements. When it was initially proposed, the idea is that to be really simple and cost efficient, in the sense having no capability of doing data decoding, right? So there's nothing behind that does in baseband any form of processing, neither a received wave for decoding, neither conversion from RF to baseband. So it's very simple. You just tune it and you reflect. Of course, in order to do that, the major question is, okay, I can reflect it, but how? So we need to control it in a way. We need to give it the right information to do this control, which, in my humble opinion, this is the major issue with this hardware. So the vision here, I'm just emphasizing an ongoing, actually, European project, RIS-XG, working in this actually concept of having smart wireless environment as a service. Actually, one of the core projects focusing completely on the technology. It started with this VisoSurf project some years ago. Then it has been, from all those years, have been a major, actually a core component of various European projects. So the idea is to code the environment in various applications with these surfaces and in a way orchestrate them together with the run that we know up to now, right? To do the optimization of the operation irrespective of what's the goal, right? Either EMBB, URLLC, or massive time communications. And here I will show a very basic example just to see that, and this was actually the idea of the smart wireless environment as a service, is that to provide performance boosted areas as is being defined by this project that I'm part of, in a way that you can have very high performance with increased locality. So I can have a very small, let's say, place, geographical area where I can boost secrecy, another that I can boost low EMF exposure, which is one of actually major requirements, especially from humanitarian, let's say, organizations, and EU is actually pushing on that, or having rates. And one example that one could think that is that like shopping malls or even train stations, right, where could be users, diverse users requesting for diverse applications. Here I'm going to show an example setup, which is actually part of this deliverable, where I have worked with a student of mine, where we have used this technology on a basic simulation setup to boost the spectral efficiency. So here you see this is a 2D plane, whereas the position of the base station here, the position of the surface, and the position of the receiver. And you will see what is happening in terms of spectral efficiency. You see the grid without having the RIS, where you can achieve, of course, has to do with the distances and the model that we're using. I'm just going to show the percentage at the end of the day. With the spectral efficiency at the given position there, which is exactly that, what we're doing, we're jointly optimizing the RIS and the base station, which is assumed to have multiple antennas. And this is what is happening when you have a RIS, meaning that you can boost this performance specifically at the position of the user by using a surface, just controlling the reflection that it provides. There's a joint optimization that happens here, and in the way you can really see that the base station, what it's actually doing apart from the direct link, is actually targeting its radiating power towards the RIS to provide this performance. So this is the idea of the performance boosted area, to be able to provide, let's say, in a geographical area, specific areas where we boost the performance. But what is this technology, which actually has very many other, let's say, terminology being used? Intelligent reflected surfaces is what Yannis said before, this IRS, the programmable hyper surfaces, as well as only using the term of metasurfaces. So they comprised of metamaterials or meta atoms. I'm just using on purpose different technology because all the papers that identify here, they play with the role with this terminology, which at the end of the day they're the same or very similar. They're usually constructed by arranging these multiple tunable elements that could be PIN diodes or varactor diodes, depending of, at the end of the day, we're going to have, in the first case, discretized states for the reflection coefficients or continuous in repeating patterns, and they're actually placed at scales that are smaller than the wavelength, especially if we are targeting applications where we want beamforming, highly dielectric beamforming. I'm saying that because in other applications, we don't really need to do that. I mean, we're not always having an environment which is quite specular. I will do my best. Quite challenging. So the shape, the geometry, the size and the orientation, the arrangement enable these smart properties capable of manipulating the electromagnetic waves. And we have actually, we can have various functionalities like blocking, absorbing, enhancing, or bending waves to achieve the actual performance. So each meta-atom of these elements or group of meta-atoms is controlled independently to achieve the desirable characteristics in terms of reflection. I need to give some hint about what is a metamaterial, which is actually any material that is engineered to have a property that is not found in naturally occurring materials. And this is actually a topic that is being actually worked by various people many years ago. And what is actually a typical example here to see is the negative index metamaterial, which is characterized by a negative index of refraction. How they work? So the impedance, which is actually the hardware characteristics of these elements, they can be modified by off-the-shelf electronic components, could be PIA and beyond, as I said before, liquid crystals, mixed electromechanical systems, or other software-defined metamaterials. And each of these elements acts locally on the phase mostly, but it could be also on the amplitude. This has certain implications on the hardware to change the characteristics of the impinging electromagnetic field. And there are available proof of concepts for beamforming, reprogramming holograms, and diffuse scattering actually are available in the field. And they can be actually very ultra low power. Here you see a typical value of this 50 microwatts per unit cell. Of course, it depends on technology, right, that people are using. Here you see one of the first works on this field work dating back to 2014, where the researchers there, they have fabricated a 0.4 square meter RIS with 102 cells operating at 2.457 gigs, actually targeting the Wi-Fi operation. And each element was very simple, only one bit of phase resolution, just changing the reflection coefficient by either 0 or pi. And here I'm just replicating two figures which are related to this technology, as was performed there, and then we emphasized it in a recent invited work for the spatial tempering focusing at a receiver Here you see in millimeter X and Y axis, and there is the receiver that is placed on the 0.0 point. And this is what happens without a RIS, and this is when we have a RIS. We use a RIS, we optimize it. I'm not going to the details of the optimization. It's actually very basic optimization, like the RIS is controlled via Ethernet, and we're just using a very simple algorithm trying to find the configuration that maximizes it. And this is what I said before about this spatial focusing. So you can have this boosting of, you can have this spatial here, but there's also temporal focusing by using an RIS. It has been also used to make channel matrices that are more Risian oriented, make them Rayleigh, increasing the effective rank of the channel, which, as we know very well, this can enable then MIMO operation, multiplexing multiple streams, which means that we can boost the spectral efficiency. And of course, there are various publications that worked on the fabrication on that and the characterization. Here you see the operation band of a specific actually fabrication example that you see here, just an image of that, which has been also used in that paper to do over-the-air computing. So it has been optimized to do the equalization, to treat the intersymbol interference over the air, which provides another application of using these surfaces, moving parts of the operation to the environment. So the environment was initially something uncontrollable, and now we use it to do processing, to do computing over the air. Of course, apart from this typical, let's say, passive, where we have this specific value for that design that I showed you before, there are certain other hardware designs. There could be RISs with reception RF chains. Here you see a theoretical work where we proposed an architecture having a single RF chain, and with some processing, we could do channel estimation and direction estimation, which is of paramount importance. I will show later on why. There are also RISs that can do simultaneous tunable reflection and sensing. This is from a recent work that the concept has been actually fabricated. So in a way, a portion of the impinging signal gets reflected tunably, and another portion gets actually becomes available in baseband to do processing. This is super relevant to do sensing, and either as a standalone or as an operation that helps the reflection, because we need this kind of control. There are reflective and transmissive RISs, where in a way, apart from having the reflective part, there's also the other portion that we can use tunable. For this, you can imagine that we have glass made of buildings, where the glass is a metasurface. The signal comes from the outer base station, and there is the transmissive RIS that directs the signal, provides this coverage extension inside the building in a cost and a power efficient way. This is still, though, theoretical, and people are still working on the feasibility of this concept. Of course, we can have RISs with reflection amplification. This is a recent paper of the recent design, where there is one equal gain amplifier that is being used. Whatever is received from, let's say, one portion of the metasurface could be amplified in the other portion of it. But of course, there are also dynamic metasurface antennas, which at the end of the day could be, they have been here envisioned to be the next generation of massive MIMO, where the antenna part, apart from being a typical antenna array, is a metasurface, and which is comprised of microstrips. These are groups of meta elements, each of them being attached to either receive or transmit RF chain to do whatever form of operation. And it has been shown in some recent theoretical works that can be much more cost and power efficient than having typical large antenna arrays with phase shifters. The application of smart wireless environments, there are many. I'm not going to go into the details, from secrecy, positioning, etc., since we're running out of time. Physical layer security, sensing, wireless power and transfer. Yannis said that before. Application, combination with other technologies like UAVs, or even using them to do this over the air that we said processing before. I mean, they can be used also to provide a form of reflection modulation. So you can convey in this mode of having tunable reflection information. I will go fast here, since this, I guess I'm already like 5 to 7 minutes. This is a basic a very interesting, actually, practical phase shift model for the operation of the metasurface of the unit cell. I want to emphasize here that there are various works with various assumptions related to that. Some are relevant to metasurfaces, some are relevant, they are not relevant to metasurfaces, some are relevant to reflector arrays. It's actually a very big and quite diverse field, but at the end of the day, I want to emphasize here a very basic formula from this expression here that tries to do this connection, and it's actually quite fascinating for those of us, some of us working on the field, where we connect what we like in signal processing, which is here the reflection coefficient. There is a connection between the hardware part of it. And here, what is actually tunable are these CN and RN parameters, which is the effective resistance and the effective capacitance, which can be tunable, and at the end of the day, determine the reflection coefficient. This can be part of an optimization problem that we can optimize according to our goal. Here, I just include a very basic model here for the RIS-Empowered communication, single antenna transmitter, single antenna receiver, the RIS, the channels, in order to give some mathematical here description on that, just to help you understand the rest of the presentation. Usually, I want to emphasize here that in practice, we have a specific set of configuration for each element. It's not continuous. We cannot do whatever we want. So usually this comprises the codebook of the cell and the codebook of the beams. And there's actually very recent work on trying to start from that and produce efficient, let's say, let them call them reflection beams from the metasurface part. I will skip a little bit here, and what I want to emphasize is the basic, which is actually widely used lately, although we're working with people just to show the weaknesses of this model, which is the baseband received signal at the receiver if you have a RIS. And what you see this famous, at least for those working in the field, cascaded channel model, where is the channel between the base station and the transmitter and the RIS. The RIS, this is the RIS and the user, and this is a diagonal matrix that contains the tunable elements of the metasurface. There are some manipulations that one can use, but at the end of the day, this is what we have here, which means that we can then devise our performance metrics and do optimization. If one thinks about multiple antenna transmitter, multiple antenna receiver, this can be generalized, and if we include also the direct channel, so we go into this form, that we can use to do our optimizations. Of course, there are other various applications having a massive MIMO base station, multiple single antenna UEs, and the surface, which has been actually elaborated in various, actually in the first works on the topic, where people, they're trying to optimize the performance. I will skip that, just in the economy of time, and I want to emphasize one of the major issues with the RIS technology and this RIS-empowered or RIS-enabled smart wireless environments is that at the end of the day, as I said before, this is a channel-dependent technology, which means in order to provide the adequate form of reflection, I need to know certain things about the channel, right? But the major issue is how I can do that if I have a RIS that is actually passive and I can not really do things. Happily, at least to myself and some other colleagues, we see lately that this hype that initially started about surfaces being passive is being abandoned, in the sense that it's really hard to do this to do this estimation, and people are actually working on various ways to provide the channel estimation. Just to go back to the mathematics, the problem here is that we want to estimate all these channels if we write down the metrics, and then we want to do optimization. But if the RIS cannot estimate, we have various issues in tackling this problem. There have been actually various approaches, control protocols, on-off activation of the elements or portions of the RIS, beam management schemes for treating passive RISs, doing explicit channel estimation or implicit, or completely going to the beam management part that are being devised. I'm just putting various papers there and the recent survey that they describe all of them. What I want to emphasize very briefly here is that the RIS is not the typical way of we use a relay, at least when we're talking about passive RIS, and one can see it in the signal model by devising what is really happening with the relay, where there is one portion here. This is what is being included if we have a relay, due to the fact that we do reception in baseband and thermal noise needs to be incorporated. You will see that in the slides. Hints here regarding the differences. RIS consist of this large number of metamaterials. Relays, though, they have typical antenna system. Of course, we can combine relays with metasurfaces. I'm just emphasizing this difference because this was one of the first things happening in the topic, just to emphasize the difference of the technology. Although personally, also with this smart repeater terminology, I see that convergence is happening. In principle, they don't require power amplification, although I showed you recent versions of people implying that about the reflection configuration. They cannot perform channel estimation and baseband signal processing. And another really, probably the most interesting thing is that they can be really large due to the fact they are cost and power efficient, which can enable near-field communications, which provide new opportunities when we're thinking not only about communications, but also localization and sensing something that was not actually present with conventional relays. This is what I implied before about doing this over-the-air equalization. And of course, there are recent works that are talking about combining this technology relay with RISs. Just to sketch some applications here, really fast. One application, which is actually one of the key scenarios being worked on this RIS-6 project that I mentioned before, is this multi-cell MIMO with a single RIS, where it is one RIS that is actually shared between base station and needs to be actually jointly optimized in these papers here. It's a typical interference management problem, right? In order to tune it to serve users, and this is very relevant for for users placed in the cell edge. Of course, it could be also multi-cell MIMO with multiple RISs. One major thing here that one could think is who owns the RIS? Could be shared, could be owned by somebody else, but the problem is that when I use a RIS to optimize my performance, I cause interference to the other. So there are certain things that operators need to take under consideration, of course, ourselves researchers. The optimization of the multi-RIS scenarios is also one of the major issues. And here I want to sketch a very recent result that we got, where we devised tools from replica theory in order to get with an expression of the average mutual information in the large number of elements regime, large number of antennas at the transmitter receiver, and large number of elements at the RIS. This is the expression here, but the interesting part is not that, is that we perform optimization on that, and we actually compared typical optimization with an optimization based on this formula, which is a closed form optimization, and we found actually some very interesting things emphasizing on a model which is quite practical, and it actually includes correlation, which is actually connected with the angular spread of the propagation in the channel. And what was actually identified at the end of the day is that, and this is actually sketched by this figure, is that it makes a lot of sense to optimize the RIS, which you can actually do it, and I will tell you later on how, when you are in regimes where you have low angular spreads, which means very highly correlated channels. But when you go to angular spreads that are actually high, closer to Rayleigh channels, performing actually optimization, this is the solid curve, doesn't provide you anything compared with just using a fixed configuration of the RIS or even doing random. This has certain implications in what? In the control of the RIS. Which means that when you are in the regime that is purely Rayleigh environment, you don't need to struggle to learn on these channels. I mean, you can have a very basic configuration, and this will do the job for you. But when you have in the low angular spread, it makes a lot of sense, and you can do two things. Either use our formula, which of course has some assumptions, but try to estimate things related to the directivity of the channel. And this is where sensing and localization kicks in, and technologies that are using RISs to perform these operations are very interesting. Apart from that, the orchestration of multi-RIS, a recent survey that we worked lately, is that the orchestration of multiple RISs here that are being attached wirelessly, Ethernet, this is not a problem here, by a controller that orchestrates the overall network. And we devised a deep reinforcement learning approach to do that. In this work, you can see the details in the economy of time, where we actually model all the components of a smart wireless environment in the DRL terminology, and we came up with an approach which has this dynamic and online learning of the configuration of the RIS with certain implications, right, of the amount of control which is needed, which means that you accumulate knowledge about the channel, about the rewards. We have various versions depending on what you need to know, right? And it has been shown that we can operate much better than the baseline, which is the random operation of the RIS. There are, of course, supervised learning approaches to tune the RIS. I'm not going to go into the details. And of course, very interesting applications where, for example, here for secrecy. What I want to emphasize here that, you know, a good technology can be always used in a bad way. So you can have the malicious RIS, as we call in this paper, and specifically here in this application, we devise an algorithm emphasizing of what the eavesdropper and the legitimate system could know, some conflicting optimization to come up. Of course, we're focusing on the legitimate part to optimize the RIS. And what we have figured out, we have seen here from our results, is that in order to be safe, that you can safeguard your communications, even when you're using beamforming and artificial noise, you should have a RIS that should be 5 times larger than a malicious RIS that an eavesdropper could use, based on the model that we use. I will be really brief here in the localization with RISs, just to emphasize a little bit what is the standard localization 3GPP. We need at least 3 synchronized base stations, line of sight connectivity to those, and limited multiple interference. What can be enabled by RISs is to have localization with line of sight, multi-RIS or near field, localization with one single antenna TX, even you will see self-localization with no TX. There is a synchronization by nature from the environment, and it's separable from uncontrollable multipath with the reflection provided by the RIS. And the RIS actually, this is the case where the RIS enables localization, but it can also boost it in a way that you have it with a typical way, but now you boost it with RISs. Providing localization, you put a RIS to provide localization in a uniform way and in dedicated boosted areas. This is actually a recent survey where I'm just including a very basic figure to show that if you're thinking typically of a case where we have a receiver here and 2 base station, we don't have the appropriate amount of degree of freedom to provide localization. Although if you even have 1 base station with 1 RIS being close in the near field with the receiver, you can have actual localization. In fact, in this paper, we identify various cases where you can have localization by having a RIS. And I want to emphasize this interesting case where we have 1 RIS, 0 base stations, and 1 user, which of course they need to be synchronized, and they need the user needs to send wideband signals, where you can have self-localization, of course, with respect of the position with a RIS. So there are many interesting applications where by incorporating a RIS, even being passive, just a simple control, you can enable localization compared to the typical cases where you will need many base stations. Apart from that, it's interesting to see the interrelation between the different hardware architecture for the RISs, right, and the applications. Here you see a localization that we perform with single receive RF RISs, which are RISs with a structure that I briefly presented before, which all the outputs of all elements are attached to a single reception RF chain. And we devised an approach where you can do this beam space music, angle estimation for the user, and then you can devised actually a line intersection approach to do localization of a user. And we actually received some very, we got some very interesting results regarding that with rather, satisfactory positioning RMSE performance, of course, for the basic model that we have in mind. Here you see actually a PEB, performance error bound contour, for the case where you have 3 RISs in the specific setup that I told you before. And you see that this is actually, this dark blue is the case where you can actually boost the performance, the localization performance, and each RIS has actually only 1 bit phase resolution for the elements. Of course, it can be also used for sensing. There are very recent works working on that. I'm only putting the figure here and showcasing how it works. So there is the radar that sends signal not only to the passive target to get the reflection, but also to the RIS in order to create an extra path. We create extra multipath at the end of the day. So it's like imposing extra degrees of freedom in the propagation channel that we can use at will to do sensing target detection at this case. Another application, this self-sensing RIS, another very recent work where the researchers there, they propose to have a controller that actually radiates a signal that will go on the RIS, will go to the target, will have a reflection, and this actually provides us the appropriate amount of degrees of freedom to perform localization. But we require RISs, a surface that has elements, these typical passive, let's say, elements only with tunable reflective coefficient, but also being coated with dedicated sensors. And another ongoing works that we're using this hybrid RIS that I presented briefly before for doing simultaneous localization and mapping without the base station. So there is the user, there is this hybrid RIS, and the user wants to identify its position and also map the environment, understand where the scatterers are. So you can actually really do it because you have the appropriate amount of degrees of freedom. So I will conclude. I hope that I convince you that there is, I will be careful what I'm going to go and say, that there are many people working on RISs and believing that they can boost the performance of wireless system in a rather cost and energy efficient manner. However, there are several challenges that need to be addressed for the technology to make it for 5G advanced and 6G. I want to emphasize once more the connection with the smart repeater, which seems to be, let's say, the initial phase of an RIS, this extra entity providing controllable reflection entering into the RAN. There are certain works, certain direction, for example, information theoretical methods to characterize the RIS-Empowered wireless channels performance in terms of capacity. When we're going about interference sound, this is something that we're working with this theoretical approach with the formula that I showed you before to study the case where we have interference. We're still thinking about algorithms and networking schemes for realizing wireless communication via RISs. So how to orchestrate multiple RISs and do optimization of their configuration. There are certain things that still are unknown in terms of modeling of the metasurface, the interaction between the elements when placed in sub-wavelength distances. I told you before, this is relevant for directive communications, and this needs to be incorporated in a channel matrix. There are actually a lot of ongoing activity on that. And certainly, we need the optimal placement of the RIS. This is super relevant for operators, for doing communication, but certainly for localization and sensing. I would like to thank you. It was not 15 minutes, but I tried my best. Thank you.
So our coffee break is a bit overdue, so maybe one question, a good one for George. I guess you presented extremely clearly. So let's take it offline then.
Okay.
And then thanks again. And we go for the coffee break. It's to be back, let's say, at 12:05 to resume with the next session. Okay, thanks.